Part 1. The Wall You Cannot See. There is a boundary around you right now, an invisible, impenetrable limit that surrounds everything you have ever observed, everything any human instrument has ever measured, every galaxy imaged by every telescope ever built, every photon of ancient light that has managed to reach us across the full age of the cosmos. This boundary is not made of matter. It is not a physical barrier in any conventional sense. You cannot approach it, cannot map its surface, cannot send a signal to find out what lies on the other side. It is a horizon made entirely of time. Every piece of light that reaches your eye has been traveling. Light moves at a fixed speed, approximately 300,000 kilometers per second, and that speed is as absolute and non-negotiable as any law in physics. Nothing travels faster. Nothing outpaces it in a vacuum. And because light has a finite speed, and the universe has a finite age, there is a maximum distance from which light could have reached us since the universe began. Not in principle, not given enough time. Right now, in this moment, with the universe 13.8 billion years old, any object farther away than the distance light could travel in 13.8 billion years simply has not had time to communicate with us yet. Its light, its radiation, its gravitational waves, all of it is still in transit, still crossing the enormous gulf of space, still not here. This is the cosmic horizon, the edge of the observable universe. Everything inside it, you can in principle see. Everything outside it, you cannot. Not because anything prevents it physically, but because causality itself does not permit it. You cannot observe what has not yet had time to send a message. The size of that observable sphere is approximately 46.5 billion light-years in radius, giving a diameter of roughly 93 billion light-years. You might immediately notice something off about that number. If the universe is only 13.8 billion years old, and light travels 1 light-year per year, how can the observable universe extend 46.5 billion light-years when the maximum travel time is only 13.8 billion years? This seems like a contradiction, and it is the kind of thing that trips people up for a long time before it clicks. The answer is space expansion. The universe is not a static container in which matter moves around while the background stays fixed. Space itself expands. The distance between any 2 points that are not gravitationally bound to each other grows over time. It has been growing since the Big Bang. So when a photon of light was emitted from some distant region 13.8 billion years ago, and that photon has been traveling toward us at the speed of light ever since, the source of that photon has not been sitting still. The space between us and that source has been stretching the entire time the photon was traveling. The photon eventually arrives because it has been moving through expanding space, and eventually the expanding space brought us close enough to catch it. But the source is now much farther away than it was when the light left. Much farther than 13.8 billion light-years. The current distance to the source is approximately 46 billion light-years, because 13.8 billion years of spatial expansion have carried it that far from us. This is not a trick or a paradox resolved by some clever accounting. It is the straightforward consequence of living in an expanding universe. The observable universe is not a sphere of radius 13.8 billion light-years. It is a sphere of radius 46.5 billion light-years. And everything inside that sphere is, in principle, available for observation by sufficiently sensitive instruments. Inside that sphere, there are estimated to be around 2 trillion galaxies. 2 trillion is 10 to the power of 12, 2 followed by 12 zeros. 2 million galaxies, each containing on average somewhere between 100 billion and a trillion stars. Each of those stars potentially hosting multiple planets. Each planet a world in its own right, with its own geology, its own chemistry, its own complex history of physical and chemical processes. The numbers within the observable universe alone are incomprehensible by any everyday measure. If you tried to count 1 star per second, starting from the beginning of time and never stopping, you would not finish counting the stars in the observable universe by the time the last red dwarf burned out, roughly 100 trillion years from now. And the observable universe is, if current cosmological models are correct, a tiny fraction of the whole. The crucial question is, whether there is more universe beyond the cosmic horizon. Not whether there is anything special there, not whether the physics changes or some exotic region of space begins, just whether space continues, whether the fabric of the cosmos, the same fabric we stand on, extends beyond the edge of what light has had time to show us. Everything we know suggests the answer is yes. The question is how much further it goes, and whether that further extent has a limit. Right now, the best answer physics can offer is this. The universe is almost certainly vastly larger than the observable portion, probably at least 250 times larger in radius, based on statistical analysis of cosmological observations, possibly much larger, and quite possibly infinite. The precise determination is complicated by the limits of measurement and by the fact that, by definition, we cannot directly observe what lies beyond our cosmic horizon. We can only infer it from the geometry we measure within the observable region and the physics we understand well enough to extrapolate. And that geometry, that physics, points toward infinity. Not certainly, not provably in the strict mathematical sense, but persistently, consistently, across multiple independent lines of evidence, in a way that grows harder to dismiss as the measurements improve. What this means is that everything you have ever seen or heard or measured, all the stars and galaxies and cosmic microwave background radiation and gravitational waves that constitute the entire observational database of astronomy, all of it is a local neighborhood, a tiny bubble within a vastness that makes the idea of scale almost meaningless. Not a sampling of the whole, not a representative cross-section, but a speck, a causal patch, a finite island in an ocean with no shore. If that is true, if the universe truly continues without end in every direction beyond our horizon, then the implications are not merely about emptiness and distance. They are about everything, about copies and repetition, and the fundamental nature of identity and uniqueness, and what it means for anything to exist. Because an infinite universe does not just mean a lot of space. It means everything that can happen, does happen. It means every possible physical configuration is realized somewhere. It means this moment, this specific arrangement of matter and energy and consciousness, is not singular and unique. It is a pattern that occurs infinitely many times in the boundless expanse beyond the edge of what you can see. That is a strange thought to sit with. Most people find it at least mildly terrifying, others find it freeing. But almost everyone, when they actually follow the logic all the way through, feels something. Because an infinite universe is not just a fact about distant empty space, it is a fact about you. If you have made it this far, and you are finding this as fascinating as I am, drop a comment below and tell me where in the world you are watching from, and what time it is there. It genuinely surprises me every time I see the range of places these videos reach. And if you have not subscribed yet, now would be a good moment. There is a lot more where this is going. Part 2. The Geometry of the Cosmos. To understand why the universe being infinite is not mere speculation, but a prediction grounded in careful measurement, you need to understand what cosmologists mean when they measure the shape of space. This is a question that sounds abstract, almost philosophical, but it has a surprisingly direct experimental answer, and that answer has profound implications. Geometry, in the familiar sense, is about surfaces and lines and the relationships between them. The geometry you learned in school, named after the ancient Greek mathematician Euclid, describes a flat surface. In flat geometry, parallel lines stay parallel forever, never meeting and never diverging. The interior angles of a triangle always sum to exactly 180 degrees. The circumference of a circle is always exactly pi times the diameter. These feel like obvious truths, simply the way things are, because every surface you encounter in everyday life is, for all practical purposes, flat. A sheet of paper, a calm lake, a freshly paved road. Your brain, built to navigate these everyday scales, registers Euclidean geometry as default, as expected, as the way space simply works. But Euclidean geometry is not the only internally consistent geometry. There are others, and they describe curved surfaces. Positive curvature looks like the surface of a sphere. On a sphere, what you might call straight lines, the shortest path between 2 points, are actually great circles, like lines of longitude on a globe. Lines of longitude are all parallel at the equator, running north and south. Parallel in the sense that they start out equidistant from each other, but if you follow them, they converge, meeting at the poles. Parallel lines on a sphere always meet, eventually. And if you draw a triangle on a sphere, by connecting 3 points with the shortest possible paths, the interior angles add up to more than 180 degrees. On a globe, if you draw a triangle with one vertex at the North Pole and 2 vertices on the equator, each of the angles at the equator is 90 degrees. The angle at the pole is also 90 degrees. That triangle's angles sum to 270 degrees. A sphere with positive curvature changes the rules. Critically, a positively curved space closes on itself. If you travel in a straight line on a sphere, you eventually return to your starting point, because the surface loops back. A positively curved three-dimensional space, the three-dimensional equivalent of a sphere's surface, would be finite in volume. Travel far enough in any direction, and you return to where you started. No edges, no boundaries, but finite. Like the surface of the Earth, which has no edge you can fall off, but is still a finite surface. Negative curvature looks like the surface of a saddle, or a leaf of kale, a surface that curves in opposite directions simultaneously. In this kind of geometry, parallel lines diverge rather than converge. A triangle on a negatively curved surface has interior angles summing to less than 180 degrees. Negatively curved space extends infinitely outward, opening up in a way that never closes. And zero curvature, flat geometry, extends infinitely in all directions without closing, like the infinite flat plane of pure Euclidean mathematics. Parallel lines stay parallel forever, because the space they traverse never curves them together. The universe must have one of these 3 geometries on its largest scales. Which one depends on the energy content? General relativity, our best theory of gravity, and the large-scale structure of space-time links the geometry of space to the energy density within it. A universe with more than a critical energy density curves positively, closing on itself. A universe with less than the critical density curves negatively, opening outward forever. A universe with exactly the critical density is flat. The critical density is a specific number, approximately 5.9 hydrogen atoms per cubic meter of space, averaged over the whole universe. That sounds extraordinarily sparse, but spread over the enormous volume of the universe, it represents an enormous total energy. The question cosmologists have been working to answer for decades is, what is the actual density, and how close is it to the critical value? The primary tool for measuring this is the cosmic microwave background, often abbreviated CMB. This is the thermal afterglow of the hot early universe, radiation that was released approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen for the first time. Before that moment, the universe was so hot and dense that it was opaque, photons unable to travel more than a short distance before being absorbed and re-emitted. At that moment of recombination, the universe became transparent, and the radiation streaming through it was free to travel without interruption. It has been traveling ever since. We receive it today, stretched by the expansion of space to microwave wavelengths, filling the sky uniformly from every direction at a temperature of approximately 2.725 degrees above absolute zero. The pattern of tiny temperature fluctuations in the CMB, variations of about 1 part in 100,000 across the sky, encodes the geometry of the universe in a measurable way. The physical size of the characteristic fluctuation pattern, the typical size of the hot and cold spots, is known from theory. The apparent angular size of those spots on the sky depends on how the light has traveled from them to us, which depends on the geometry of space. In a positively curved universe, the spots appear larger than they should. In a negatively curved universe, they appear smaller. In a flat universe, they appear exactly the expected size. The Planck satellite, which produced the most precise map of the CMB to date, measured these angular scales with extraordinary precision. The result? The universe is flat, to within a measurement uncertainty of about 0.4%, not curved, not slightly curved, flat, with a precision that would require the universe's energy density to be within 0.4% of the critical value, with subsequent measurements driving the constraint even tighter. This flatness is itself remarkable and requires explanation, which brings us to inflation, but we will get there. For now, the point is the consequence. A flat universe that has no non-trivial topology, no unusual looping or identifying of distant regions, is infinite. A flat, simply connected universe extends without limit in all directions. No boundary, no edge, no point at which the geometry gives way to something else. Just space, going on. The Planck satellite also searched for evidence of non-trivial topology, looking for the kind of repeating patterns in the CMB that a universe which loops back on itself would produce, the cosmic equivalent of standing between two mirrors and seeing a corridor of reflections stretching away. No such repeating patterns were found. The observable universe shows no topological signatures that would indicate a closed structure. If the universe is finite and topologically closed, it must be at least 400 times larger than the observable universe in diameter to have evaded detection. Some statistical analyses, using a method called Bayesian model averaging to compare different cosmological models against the data, found that the universe is at minimum about 250 times larger than the observable universe, which corresponds to a minimum diameter of about 7 trillion light-years. And those are the lower bounds from statistical inference. The true size could be vastly larger, and the most natural interpretation of the flat geometry, the simplest model consistent with the measurements, is that the universe is simply infinite. Let that specific claim sit with you for a moment, because it is easy to say and hard to feel the weight of. Not that the universe is very large, that the universe is infinite, that it does not have a total size, that the concept of how big the universe is does not have a numerical answer, because the answer is not a number. The answer is that there is no answer, because the extension continues without terminus, in every direction, at the same density of matter and radiation and dark matter and dark energy that fills the observable universe. Infinite space means infinite galaxies, infinite stars, infinite planets, infinite configurations of matter, infinite chances for every arrangement of atoms that the laws of physics permit to occur. And this is where the geometry becomes something more than a measurement and starts to say something about the nature of existence itself. There are a finite number of ways that a region of space the size of the observable universe can be arranged. A very large finite number, but a finite one. Tegmark's calculation places this number at around 10 to the power of 10 to the power of 115. If the universe contains an infinite number of regions of that size, the pigeonhole principle, one of the simplest ideas in all of mathematics, guarantees that every possible arrangement must be repeated, infinitely many times, including every arrangement that contains a planet like Earth, including every arrangement that contains a version of you sitting where you are sitting. The geometry of the cosmos, measured with a satellite, implies that you have infinitely many exact copies. Part 3. The machine at the beginning of time. The universe being flat is not an obvious or inevitable feature. It is a property that, if you trace it back to the early universe, becomes increasingly remarkable the closer you look at it. A universe that is flat today, 13.8 billion years after the Big Bang, would have needed to be extraordinarily precisely flat in its earliest moments. Not approximately flat, extraordinarily flat, fine-tuned to a degree that is uncomfortable to contemplate without a mechanism to explain it. This is called the flatness problem, and it is one of the motivations that drove the physicist Alan Guth, then a young postdoctoral researcher at SLAC and later at Cornell, to develop the theory of cosmic inflation in 1979 and 1980. To understand why flatness is a problem, imagine a pencil balanced on its point. A perfectly balanced pencil could, in theory, stand upright indefinitely. But the slightest deviation from perfect vertical, any tiny perturbation at all, causes it to fall away from the balanced state and never return to it. The balanced state is unstable. Real pencils fall because real pencils are never perfectly balanced, and because the real world always provides tiny perturbations. The flatness of the universe is similar in its dynamics. In the standard Big Bang model without inflation, a universe that begins with even a tiny departure from perfect flatness, a tiny positive or negative curvature, does not stay near flat. The curvature grows over time. A tiny positive curvature in the very early universe would have grown and grown, leading to a universe that recollapsed into a big crunch long before stars could form. A tiny negative curvature would have grown and grown, leading to a universe that expanded so rapidly it never formed any structure. For the universe to be as flat as we observe it today, after 13.8 billion years of evolution, the flatness would have needed to be set to within 1 part in 10 to the power of 62 at the time of Big Bang nucleosynthesis, the era when the lightest atomic nuclei were forged. That is a precision comparable to balancing the pencil not just within a millimeter of vertical, but within the width of a proton. This does not make the flatness impossible, but it demands an explanation. Why was the universe so precisely flat at the beginning? Standard Big Bang theory provides none. Guth's inflation provides one. The essential mechanism of inflation is a period of extremely rapid, exponential expansion in the very early universe, driven by a hypothetical field called the inflaton. The inflaton occupies every point of space with a large, roughly uniform energy density. This energy density creates a negative pressure, which in general relativity has the effect of driving exponential expansion. Space doubles in size, then doubles again, on a timescale so short that the doubling happens perhaps 100 times or more in a fraction of a second. The volume increases by a factor of 2 to the 100th power, which is roughly 10 to the 30th, in what is essentially no time at all by human standards. What does this exponential stretching do to the flatness? Think about a sphere. If the sphere is the size of a marble, you can clearly see its curvature. Hold it in your hand, and the roundness is obvious. Now imagine inflating that marble to the size of the Earth. What was obvious curvature is now imperceptible. The surface looks flat to any measurement you could perform on a local scale. You know it is curved because you know it is a sphere, but the measurements themselves show almost no detectable curvature. Inflation does this to the curvature of space. Whatever curvature existed before inflation, positive or negative, however large or small it was, inflation stretches it to an extent where any local measurement shows a geometry indistinguishable from perfectly flat. The residual curvature after inflation is suppressed to a level far below anything any measurement could detect. The flatness we observe today is not a coincidence. It is the expected aftermath of an epoch of exponential expansion that erased whatever initial curvature existed. Inflation also solves a second puzzle, the horizon problem. Look at the cosmic microwave background in one direction. Look at the CMB in the exact opposite direction, on the opposite side of the sky. The temperature in those two directions is the same, to within 1 part in 100,000. Now ask, was there any time in the history of the universe when those two regions could have been in causal contact? Could they have exchanged information, shared heat, equilibrated to the same temperature? In the standard Big Bang model without inflation, the answer is no. Those regions are separated by an enormous distance, and the universe has not been old enough for light to travel from one to the other. There has been no time for them to equilibrate. Their identical temperatures cannot be explained by any causal process in the standard model. You are left simply asserting that the initial conditions of the universe happen to produce the same temperature everywhere, which is an unsatisfying answer that feels like it is wishing the problem away rather than explaining it. Inflation explains it because it asserts that the entire observable universe, everything we can see in any direction, grew from a single tiny patch of space before inflation began. That patch was small enough, and the pre-inflationary universe was old enough, that the patch had been in causal contact and had fully equilibrated. It had the same temperature everywhere because it had time to reach thermal equilibrium in its small pre-inflation form. Then inflation stretched that tiny, uniformly tempered patch to the enormous scale of the present observable universe. The uniformity we see is not a coincidence of initial conditions. It is an inheritance from a single small, well-mixed region that was then inflated to cosmic scale. The small deviations from perfect uniformity, the 1 part in 100,000 temperature variations in the CMB, are explained by quantum mechanics. Quantum fluctuations in the inflaton field during inflation are random, tiny, inherent to the quantum nature of any field, and they are frozen into the fabric of space as the inflaton field rolls toward its minimum and inflation ends. These tiny quantum ripples, stretched to cosmological scale by the inflation, became the seeds of large-scale structure. The overdense regions eventually collapsed under gravity to form galaxies, galaxy clusters, the enormous filaments and voids of the cosmic web. The pattern of those fluctuations has a specific statistical signature predicted by the simplest models of inflation, and the CMB measurements from WMAP and Planck match those predictions with extraordinary precision. This is some of the strongest evidence that inflation actually occurred. But now comes the feature of inflation that nobody asked for and many people still find uncomfortable. Inflation, as described above, begins in a tiny region of the early universe, and then ends when the inflaton field rolls to its minimum, releasing its energy as heat and particles, reheating the universe, and beginning the hot Big Bang era. In this picture, inflation is a single event. It starts, it expands space enormously, it ends, and the result is our universe. This is not what most versions of the inflaton field actually predict. The quantum nature of the inflaton field means that different regions of space experience slightly different conditions. In most regions, the field rolls steadily toward its minimum, inflation ends, and a pocket of ended inflation forms. But quantum fluctuations can push the field back up toward higher values in some regions. In those regions, inflation continues. More than that, because inflation is exponential, those still inflating regions expand so rapidly that they come to dominate the total volume of space, even as individual pockets of ended inflation are produced. The total volume of still inflating space grows faster than inflation converts it to ended inflation pockets. The result is a process that never terminates. Alan Guth described this as eternal inflation. Once inflation starts, it continues globally, producing pocket universes, including ours, at a relentless and unending rate, not finishing when enough pockets have been produced, not winding down, but going on forever, because the still inflating background always grows faster than it produces stopped inflation regions. Guth himself has stated this in explicit terms. In an eternally inflating universe, anything that is physically allowed will ultimately happen, and it will happen an infinite number of times. This is not a side note. It is the central feature. Eternal inflation is not a universe that produces a lot of pocket universes. It is a universe that produces an infinite number of them, guaranteed, because the process never stops. Our universe, with its 13.8 billion years of history, and its 2 trillion galaxies, and its carbon and oxygen and planets and people, is one of those pockets. One island of ended inflation in a background that is still inflating, still producing new pockets, and will never stop. The other pockets, the other bubble universes produced by eternal inflation, are outside our cosmic horizon. We cannot observe them. The bubble walls, the boundaries between different regions of ended inflation, are receding from us faster than light, because the still inflating space between us is expanding. We will never receive a signal from them. They are causally disconnected from us in the strongest possible sense. But they exist. Or at least, if inflation happened, and the evidence strongly suggests it did, they almost certainly exist, and there are infinitely many of them. Part 4. The numbers that should not make sense. There is a way to calculate the distance to your nearest exact copy in the universe. Not an approximate copy, not a version of you who is mostly you but made different choices or grew up in a different city. An exact copy, every atom in the same place, every synapse carrying the same weight, every memory, every scar, every preference, every thought you are currently having, exactly replicated. The physicist Max Tegmark did this calculation, and it is worth understanding how it works, because it reveals something deep about what infinity actually means for physical existence. Start with the observable universe. It contains approximately 10 to the power of 80 atoms. This is a finite number. It is an inconceivably large number from a human perspective, but it has a ceiling, a definite upper bound. If you imagine all of those atoms as binary choices, each atom either present or absent in a given position, the number of possible configurations of matter in a region the size of the observable universe is 2 to the power of 10 to the 80. That is an astronomically larger number, but still finite. A more careful quantum mechanical treatment, accounting for the fact that particles have continuous position and momentum, uses the concept of the Bekenstein-Hawking entropy bound, which sets a maximum amount of information any region of space can contain. For a region the size of the observable universe, this bound gives a maximum of approximately 10 to the power of 10 to the power of 115 distinct quantum states. This is the total number of distinguishably different things a region of space that size can be. Now, if the universe is infinite and homogeneous, meaning the same physics and similar density of matter everywhere, then the number of observable universe-sized regions within the total universe is infinite. There are infinitely many patches of space, each the size of our observable bubble. Each of those patches has at most 10 to the power of 10 to the power of 115 possible configurations to occupy. Finite menu. Infinite containers. By the pigeonhole principle, every configuration is realized infinitely many times, including the one that contains you. Tegmark then asked, how far away is the nearest patch that contains an exact duplicate of the entire observable universe? This is a statistical calculation. How many distinct patches do you need to sample before you have, by probability, exhausted all configurations, and the first repetition occurs? The answer is approximately 10 to the power of 115 patch diameters, because you need to sample enough patches to exhaust the configuration space. Each patch is roughly 93 billion light-years across. Multiply. The result is that your nearest exact cosmic duplicate is approximately 10 to the power of 10 to the power of 115 meters away. This number is so large that human language has no vocabulary for it. The number of atoms in the observable universe is 10 to the 80. The diameter of the observable universe is about 10 to the 26 meters. The number 10 to the power of 10 to the power of 115 makes both of those look like nothing. It makes a googolplex, 10 to the power of a googol, look like nothing. It is in every practical sense beyond imagining, but it is finite. It is a specific distance. It is not infinitely far away. And in a universe that extends infinitely, an enormous but finite distance is not a barrier. It just means very, very far. A simpler calculation gives the nearest copy of just you, not the entire observable universe, just an exact duplicate of your body, your brain, your current state of mind. Tegmark estimates this at approximately 10 to the power of 10 to the power of 29 meters. Still incomprehensibly distant, but dramatically closer than the full universe copy. What should you make of this? On one reading, nothing. These copies are so far away that they will never interact with you. No signal will ever pass between you and your nearest duplicate. For all practical purposes, concerning any causal influence on your life, they might as well not exist. But existence is not the same as influence. The question of whether your copy exists is not the same as the question of whether it matters to your immediate decisions. Your copy exists the way a distant star exists. You will never visit it. It will never affect you directly. But it is real, physical, actual, a genuine configuration of matter occupying genuine space, following genuine physical laws, having genuine experiences. And if the universe is infinite, as the physics suggests, then there is no way around it. The copy is there. More than there. There are infinitely many copies. Not a huge number of copies. Not a very large number. An infinite number. Infinitely many exact duplicates of you, right now, each experiencing this same moment, thinking this same thought, and each, from inside their own experience, feeling exactly as unique and singular as you feel. The concept of uniqueness, of being the only one, is a local concept. It is true within the observable universe. Within your cosmic horizon, there is no other you. Within the 93 billion light-year bubble of space from which you can receive information, your specific configuration of atoms almost certainly exists exactly once. The observable universe is large enough that repetition of anything as complex as a human brain is not expected within it. Your uniqueness, within the observable region, is genuine. But the observable region is not everything. It is a tiny fraction of everything. And outside it, the copies are there, as real as you are, in a space so vast that the word vast has no adequate amplification. And then there are the near copies. At distances somewhat further than your nearest exact duplicate, the copies start to diverge. The universe up to this moment might be identical, but then a single quantum event goes differently. A photon takes a slightly different path. A neuron fires at a slightly different moment. A mutation does or does not occur. A choice is made differently, and that copy starts to live a different history from yours. Slightly at first, then increasingly, as small differences propagate through time and complex systems amplify tiny perturbations into large outcomes. At greater distances still, you find versions of yourself who made a completely different decision at some critical juncture. Took a different job, lived in a different city, made or missed a connection that changed the entire direction of a life. Read a different book at 14, had a different conversation with someone who mattered. All of these are real people. Real minds, real experiences, real lives, embedded in real physical space, separated from you not by any metaphysical boundary, but purely by distance. The multiverse, in this most basic and least speculative form, is not a science fiction concept. It is the straightforward implication of infinite flat space combined with the finitude of possible configurations. Part 5. The landscape at the end of physics. The copies described so far all exist within a multiverse that shares the same physics. Same speed of light, same gravitational constant, same mass of the electron, same fine structure constant, same cosmological constant. The same laws, playing out in different regions of the same infinite space, just sampling all possible configurations of matter within those shared laws. But eternal inflation suggests something further, and considerably more radical. When inflation ends in a pocket universe, the inflaton field rolls down to a stable low-energy configuration. In our universe, this produced the specific particle physics we observe, the specific masses of the quarks, the specific strengths of the electromagnetic, weak, and strong nuclear forces, the specific value of the cosmological constant, the specific number of large spatial dimensions, which is 3. Everything that makes our physics what it is. But in string theory, which currently represents the most developed mathematical framework for unifying quantum mechanics with gravity, the number of possible stable low-energy configurations of the underlying theory is estimated to be around 10 to the power of 500. This is called the string landscape. Each different stable configuration corresponds to a different effective physics at low energies, a different set of physical constants, a different particle content, potentially even a different number of large spatial dimensions. When inflation ends in different pocket universes, it may end with the inflaton field rolling to different minima in this landscape. Different pockets of ended inflation, different bubble universes, may find themselves with entirely different physics. Not just different arrangements of the same atoms, but different atoms, different particles, different forces, different constants. This is the Level 2 multiverse in Tegmark's framework, a collection of pocket universes, each potentially with different physical laws. Our universe is one bubble with one specific set of physical constants. Other bubbles, out beyond our horizon in the eternally inflating background, may have completely different physics. A universe where the fine structure constant is slightly different, and chemistry as we know it does not work. A universe where the cosmological constant is 100 times larger and space expands so fast that no galaxies ever form. A universe with 4 large spatial dimensions instead of 3. A universe where the proton is heavier than the neutron and stable hydrogen does not exist. Most of these universes are sterile. Their physics does not permit the organized complexity that we associate with life, or possibly even with any interesting structure at all. They are dark, cold, featureless, or unstable, collapsing before anything interesting happens. But in an infinite landscape with infinitely many pocket universes being produced, the fraction that permit complexity is itself infinite. And among those infinitely many complexity-permitting universes, the range of what is possible encompasses an enormous variety of structures, life forms, and potentially minds. We find ourselves, apparently, in a universe with the specific physical constants that permit us to exist, and the question of why those constants have the values they have, rather than any of the vastly larger number of values that would produce a sterile universe, is one of the deepest unsolved problems in physics. The question is called the fine-tuning problem. Part 6. The numbers that should not work. The fine-tuning problem is not a vague philosophical observation that the universe seems designed. It is a collection of specific, quantified, experimentally verified facts about the values of physical constants, each of which sits in a narrow range that permits complex structure to exist, and each of which could, as far as the current underlying theory tells us, have been different. Begin with the cosmological constant. This is the energy density of empty space, the vacuum energy, which in general relativity acts as a uniform background energy that affects the expansion of the universe. Its measured value is approximately 10 to the minus 122 in natural Planck units. When you ask quantum field theory, our best current theory of matter and forces, to predict this value from first principles, it gives an answer near 1 in Planck units, arising from the zero-point energies of all quantum fields summed over all modes. The discrepancy between the prediction and the measurement is 122 orders of magnitude. This is not a small disagreement. It is the largest discrepancy between theoretical prediction and experimental measurement in the history of physics. Steven Weinberg, who won the Nobel Prize in Physics in 1979, has called it the worst prediction in the history of science. The predicted value and the measured value differ by 10, followed by 121 zeros. Something in the underlying physics is canceling almost all of the quantum vacuum energy, leaving only a tiny remnant. Nobody knows what that something is. It is one of the central unsolved problems in theoretical physics. But here is the fine-tuning aspect. If the cosmological constant were larger, not by 122 orders of magnitude, but by just a few orders of magnitude, the universe would have expanded so rapidly after the Big Bang that matter would never have had time to gravitationally collapse into galaxies or stars or planets. The cosmic expansion would have won the battle against gravity long before any structure could form. A universe with a cosmological constant 100 times larger than the observed value would be a universe of structureless gas, rapidly dispersing in an accelerating expansion with no galaxies, no stars, no planets, no chemistry, nothing. If the cosmological constant were negative, which is also theoretically possible, the universe would have recollapsed into a hot singularity within a short time after the Big Bang, again before any structure could form. The range of cosmological constant values that permits complex structure is extraordinarily narrow, and the observed value sits, with no apparent reason, within that narrow range, not near the edges of it, precisely within it, in a way that maximizes the time available for structure to form and survive. The strong nuclear force provides another example. This is the force that holds quarks together inside protons and neutrons, and holds protons and neutrons together inside atomic nuclei. Its strength, measured by the coupling constant of the strong force, is a dimensionless number approximately equal to 0.12 at typical energy scales. If this value were a few percent larger, protons would fuse into diprotons, two-proton nuclei, so readily in stellar cores that stars would burn through their hydrogen fuel almost instantaneously, rather than over billions of years. There would be no long-lived stars, no stable solar systems, no time for planets to form and complex chemistry to develop. If the strong coupling constant were a few percent smaller, nuclei with more than one proton would be unstable. Atomic physics would stop at hydrogen. The entire periodic table beyond element 1 would not exist. No carbon, no oxygen, No nitrogen, no iron, no silicon. The chemistry of life, and indeed of any complex material, would be impossible. The ratio of the electromagnetic force to gravity is another critical number. Electromagnetism is approximately 10 to the 36 times stronger than gravity at the scale of atoms. This enormous ratio, which looks puzzling rather than natural, is actually necessary. If gravity were much stronger relative to electromagnetism, stars would form more quickly, burn more intensely, and have much shorter lifespans, potentially too short for planetary systems to develop complex chemistry. If gravity were weaker relative to electromagnetism, stars would not form at all. The balance between them determines the mass range of stars and the timescales on which they operate. The mass ratio of the proton to the electron, approximately 1,836, governs the geometry of atomic orbitals and the nature of chemical bonds. The electron is light enough to occupy a diffuse orbital cloud around the nucleus. If it were much heavier, atoms would be much more compact, and chemistry would behave differently. If it were much lighter, atoms would be too large and diffuse for chemical bonds to operate at the scales needed for molecules. There are perhaps 30 or so parameters in the standard model of particle physics plus cosmology, each measured but none derived from more fundamental principles. And for a significant fraction of them, the observed value appears to sit in a range that permits complexity, while even modest deviations would produce a universe incapable of forming stars, atoms, or anything interesting. This is the fine-tuning problem. It is real. It is quantified. It is not a matter of philosophical preference, and it has three serious classes of response. The first is that future physics will explain the values. A true theory of everything, perhaps some form of quantum gravity or a completed string theory, might derive the standard model parameters from more fundamental principles, showing that the values we measure are the only ones consistent with a self-consistent theory. In this scenario, the fine-tuning is apparent rather than real. The constants could not have been different because the underlying theory forces them to be what they are. This is possible. It would be extraordinary. No such derivation exists today. The second response is the multiverse. If all possible values of the constants are realized in different pocket universes produced by eternal inflation, then there is no fine-tuning mystery. The constants take all possible values somewhere. We find ourselves in a universe where they permit our existence, because we could not exist in a universe where they do not. This is the anthropic explanation. The selection effect of conscious observation does the work of explaining why we observe life-permitting values. We see these values not because they were aimed at, but because we exist, and our existence requires them. This explanation is controversial. Many physicists find it satisfying. Others find it empty of content, arguing that it is a logical triviality dressed up as a physical explanation. The debate continues, and it will not be settled until either the multiverse is confirmed or a deep theoretical explanation for the constants is found. The third response is that there is no explanation, and no explanation is needed. The constants have the values they have. We live in a universe with these values. There is no deeper reason. This is sometimes called the brute fact position, and while it is philosophically coherent, most physicists find it intellectually unsatisfying. Science proceeds by asking why, and answering because that is how it is, does not feel like an answer. What all three positions share is the acknowledgement that the fine-tuning is real. The numbers are what they are, they permit us, and why they do, in any deep sense, is unknown. Part 7. The Dark Force and the Accelerating End. In 1998, the universe changed its story. Not in any physical sense, but in the sense that our understanding of what the universe is doing underwent a revision so dramatic that it overturned the assumptions of most working cosmologists at the time. Two independent teams were measuring the distances to Type Ia supernovae, stellar explosions so bright that they can be seen across billions of light-years. These supernovae are useful precisely because they always explode with approximately the same intrinsic brightness, making them what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears to be, you can calculate how far away it is. Dimmer means farther. Brighter means closer. The teams were using this technique to measure the expansion history of the universe. The idea was to compare the distances to distant supernovae with their recession velocities, measured by the redshift of their light, and from that comparison, extract the rate at which the expansion of the universe was changing over time. The prediction from a universe dominated by matter was straightforward. Gravity is attractive, matter pulls on matter, and the expansion of the universe should be slowing down. You put in the numbers, you measure the deceleration rate, and you learn something about the density of matter in the universe. Both teams found the same thing. The distant supernovae were dimmer than expected. Not much dimmer, not dramatically dimmer, but consistently, significantly dimmer, in a way that both teams independently confirmed. Dimmer means farther away than expected. And farther away than expected means the universe has been expanding faster than the simple matter-dominated deceleration model predicted. The expansion is not slowing down. It is speeding up. The universe is not decelerating under gravity. It is accelerating. Something is pushing space apart. Something other than matter, other than radiation. Something that does not dilute as space expands. Something that exerts a persistent outward push that grows in relative dominance as the matter density of the universe dilutes with expansion. This was named dark energy, and its discovery won the 2011 Nobel Prize in Physics for Saul Perlmutter, Brian Schmidt, and Adam Rees. The simplest model of dark energy is Einstein's cosmological constant, the energy density of empty space. If the vacuum itself carries a small but non-zero energy density, and if that energy density does not dilute as space expands, because the energy is a property of space itself, not of matter or radiation within it, then as the universe expands and the matter density drops, the vacuum energy eventually dominates the total energy budget and drives accelerating expansion. This is precisely what the observations show. The current standard model of cosmology, lambda CDM, incorporates the cosmological constant and matches an extraordinary range of observations with high precision. Dark energy constitutes approximately 68% of the total energy content of the universe. Dark matter, the mysterious non-luminous gravitating substance that holds galaxies together and whose particle nature remains unknown, constitutes about 27%. Ordinary matter, everything made of atoms, everything ever seen with any telescope, everything we have ever directly detected or interacted with, constitutes only about 5% of the universe's total energy content. We are, in a precise quantitative sense, the minority. The cosmos is mostly made of things we cannot directly observe and do not understand. The consequences of dark energy for the long-term future of the universe are severe. In a universe dominated by the cosmological constant, the expansion continues and accelerates indefinitely. Galaxies that are currently within our observable universe will eventually be carried beyond our cosmic horizon by the expansion, disappearing from view not because they cease to exist, but because the space between us and them grows faster than light can cross it. The universe we can see will shrink over cosmological time. Millions of years from now, the expansion will have accelerated enough that the farthest galaxies we currently observe will have crossed the horizon. Billions of years from now, only the local group of galaxies, those gravitationally bound to the Milky Way, will remain visible against the darkness. The rest will have been carried away into an inaccessible distance. The night sky of the far future universe will be nearly empty. The light of 2 trillion galaxies that we can currently catalog will have been stretched to invisibility by the expansion, their sources receding beyond the reach of any telescope. A civilization in the far future, looking up at the night sky, would see only a handful of bound galaxies and might reasonably conclude that those were the whole of the universe. The evidence that the cosmos is far larger, the signatures of distant galaxies that we take for granted today, will simply not be available. They will have been carried away. This is a sobering thought about knowledge and about the contingency of our cosmic moment. We happen to exist at an epoch when the universe is still young enough, and the expansion still slow enough, that the observable sky is rich with evidence of the universe's history and extent. In the far future, that evidence will be gone. Not destroyed, just inaccessible. The universe will not change its nature. Our view of it will shrink. This accelerating expansion also raises questions about whether the dark energy is truly constant or whether it evolves with time. The DESI survey, the Dark Energy Spectroscopic Instrument, completed a major data release in 2024 and 2025 that has provided the most precise measurement of dark energy's evolution over cosmic time to date. The preliminary results, which have attracted considerable attention in cosmological circles, suggest some tension with the simplest cosmological constant model, hinting that the dark energy equation of state may have evolved over cosmic time. These results are not yet at the level of statistical significance that physicists would call a confirmed discovery, and they may be revised by future data. But if they hold up, they would imply that dark energy is not a simple cosmological constant, but a dynamical field, something that changes as the universe evolves. A dynamical dark energy, particularly of the phantom variety, where the energy density increases over time, leads to more dramatic consequences. In phantom dark energy models, the strength of the dark energy grows without limit, eventually overcoming every binding force in the universe, from gravitational bonds holding galaxy clusters together down to the electromagnetic bonds holding atoms together. The result is the Big Rip, a scenario in which the expansion rate grows without bound and, in a finite time, tears the universe apart at every scale. Some estimates place the Big Rip at approximately 20 to 22 billion years from now, if the dark energy equation of state is in the phantom regime. In the Big Rip scenario, the sequence of destruction follows a well-defined progression. Galaxy clusters are torn apart first, their gravitational bonds overwhelmed by the expanding dark energy, perhaps 100 million years before the final singularity. Individual galaxies follow, then solar systems, as the expansion overrides the weaker gravitational bonds between stars and planets. In the final minutes, planetary surfaces are pulled apart, then atoms are ionized, then atomic nuclei are disrupted, and in the final fraction of a second, even the fabric of spacetime itself is torn asunder in a singularity of infinite expansion rate. It is a dramatic end. Whether it is the actual end is not known. Current data do not firmly establish that dark energy is in the phantom regime. The most likely scenario, based on current measurements, is still an indefinitely expanding universe tending toward heat death. But the uncertainty in the dark energy equation of state leaves room for the more violent alternative, and the fact that we do not know which fates awaits is itself a remarkable statement about the limits of current knowledge. Part 8. The brains that shouldn't exist. There is a problem with infinity that does not show up in ordinary life, and does not become apparent until you take seriously the idea of a universe that lasts forever. It is called the Boltzmann brain problem, and it is genuinely disturbing in a way that takes a moment to appreciate. It is not disturbing in the sense of being emotionally upsetting. It is disturbing in the sense of being a coherent logical consequence of accepted physical principles that seems to undermine the reliability of your own observations about reality. Ludwig Boltzmann was an Austrian physicist working in the second half of the 19th century. He was one of the founders of statistical mechanics, the framework that explains macroscopic thermodynamics in terms of the statistical behavior of enormous numbers of molecules. His key insight was that the second law of thermodynamics, the law that entropy always increases, that systems always tend toward disorder, is a statistical law rather than an absolute one. It holds not because individual molecules are required to move toward disorder, but because disordered states are so vastly more numerous than ordered states that random motion almost always leads toward disorder. The qualifier almost always is important. Statistical laws have exceptions. Fluctuations are possible. A gas of molecules in a box will, overwhelmingly almost always, be uniformly distributed throughout the box, because a uniform distribution has by far the highest entropy. But occasionally, very rarely, the random motions of molecules will conspire to produce a fluctuation, a brief moment where the gas spontaneously moves toward one corner. This is not impossible. It is merely extraordinarily unlikely. Boltzmann extended this thinking to cosmology and ran into a serious problem. If the universe is eternal and reaches a state of maximum entropy, thermal equilibrium, and then fluctuates randomly around that equilibrium forever, then over a sufficiently long time, any fluctuation that is physically possible will eventually occur, including fluctuations far, far more improbable than a gas spontaneously compressing to one corner of a room. Given enough time, a random fluctuation could produce a galaxy, or a solar system, or a planet, or a brain. The philosopher and physicist Sean Carroll explored this in the context of modern cosmology and gave it a contemporary form. In a de Sitter universe, the late-time universe dominated by the cosmological constant, the space has a finite temperature called the Gibbons-Hawking temperature, arising from quantum effects near the cosmic horizon. This temperature means the universe is not perfectly still and zero energy. It fluctuates. Quantum fluctuations occur, and over an infinite time, those fluctuations can produce anything with non-zero probability, including a brain. A Boltzmann brain is a hypothetical observer that spontaneously assembles from random thermal fluctuations in a high-entropy universe. The probability of any particular brain assembling is astronomically small, requiring the precise arrangement of an enormous number of particles by chance. But the universe, in the heat-death scenario, lasts forever, and in infinite time, any event with non-zero probability must occur, infinitely many times. Here is the genuinely disturbing part, which is more likely to occur in the full history of the universe. An ordinary observer, a brain that arose through 13.8 billion years of cosmological evolution, culminating in planets and chemistry and biology and neurology, or a Boltzmann brain, a brain that spontaneously assembled from a random fluctuation in a vast, cold, empty universe. The ordinary observer requires an extraordinary sequence of unlikely events. The Big Bang needed to produce precisely the right initial conditions. Stars needed to form. Heavier elements needed to be produced in stellar interiors. Planets needed to form around a stable star. Life needed to arise from chemistry. That life needed to evolve toward increasing complexity. That complexity needed to produce nervous systems and ultimately consciousness. The probability of any given observer arising through this causal path is tiny. A Boltzmann brain also has a tiny probability. Much tinier, in fact, for any given moment of fluctuation. The probability of a brain spontaneously assembling from thermal noise is less than the probability of every molecule in a room spontaneously moving to one corner simultaneously, by many orders of magnitude. But here is the twist. The number of opportunities for a Boltzmann brain is vastly larger. The universe lasts for perhaps 10 to the power of 100 years during the black hole epoch alone, and potentially forever in the de Sitter phase. The number of moments in which a Boltzmann brain fluctuation could occur is incomparably larger than the number of moments during the structured era of the universe in which ordinary observers arise. Even if ordinary observers are far more likely per unit time than Boltzmann brains, the sheer duration of the Boltzmann brain era overwhelms the comparison. In a universe that lasts forever and ends in a low-temperature de Sitter phase, Boltzmann brains eventually vastly outnumber ordinary observers by a margin so enormous that the probability of you, right now, being a Boltzmann brain rather than an ordinary observer would be essentially 1. You would be more likely to be a random fluctuation with false memories of a past that never happened than to be a causally evolved organism with a genuine history. This is a reductio ad absurdum. The conclusion is absurd, which means something in the premises must be wrong. But which premise? Physicists and cosmologists take different positions. Some argue that the problem shows that eternal de Sitter space is physically impossible, and that the true late-time universe must find a different fate. Some argue that the probability calculation is wrong, that the measure problem in eternal inflation invalidates the comparison. Some argue that Boltzmann brains cannot actually be produced in quantum gravity frameworks even given infinite time, because the vacuum state is genuinely stable and does not fluctuate in the relevant way. None of these arguments is settled. The Boltzmann brain problem is not a curiosity at the fringe of physics. It is cited in serious cosmological literature as a constraint on models. Any cosmological model that predicts Boltzmann brains will eventually dominate the observer count is, among many researchers, considered to have a genuine problem that requires resolution. What the Boltzmann brain problem reveals is a deeper issue with infinite time and infinite space. The mathematical machinery of probability, developed for finite systems over finite times, starts to produce strange and unreliable results when applied to infinite universes. The problem of defining what is typical or expected or probable in a universe where everything that can happen does happen infinitely many times is called the measure problem, and it is one of the deepest unsolved conceptual problems in modern cosmology. It is not a technical gap to be filled in. It is a genuine conceptual challenge about how to think about probability and typicality in an infinite setting. The infinity of the universe is not just a large number. It is a category that breaks the standard tools of reasoning in ways that matter. Part 9. The End of All Things, and What Comes After. Let us take the long view, the very long view. Right now, the universe is in what cosmologists call the stelliferous era, the age of stars. It is a period of extraordinary activity, of nuclear fusion powering billions of stars across trillions of galaxies, of radiation flooding the cosmos, of rocky planets orbiting those stars in the narrow habitable zones where liquid water can persist, and chemistry can do interesting things. This era began roughly a few 100 million years after the Big Bang, when the first stars ignited from the collapsing primordial gas, and it will last until the last red dwarf star exhausts its hydrogen fuel and fades to cold darkness. The last red dwarfs, the most numerous class of stars in the universe, burn so slowly and so efficiently that they will continue shining for approximately 1 to 10 trillion years from now. 1 trillion years is about 70 times the current age of the universe. For the next trillion years, give or take, the universe will continue to contain burning stars, will continue to have the possibility of planets bathed in starlight, will continue to be the kind of place where something like life could potentially exist. After the last red dwarf, the universe enters what is sometimes called the degenerate era. No more active nuclear fusion anywhere. No more new light being generated. The universe is populated by stellar remnants, white dwarfs, the compact, slowly cooling Earth-sized cores of stars like the Sun, fading from white to yellow to red to dim infrared, and eventually to cold black, over hundreds of billions to trillions of years each. Neutron stars, the collapsed cores of more massive stars, spinning rapidly and gradually slowing. Black holes, the collapsed cores of the most massive stars, ranging from a few solar masses for stellar mass black holes to billions of solar masses for the supermassive black holes at the centers of galaxies. Also present in the degenerate era, a population of objects that never ignited, brown dwarfs, failed stars that accumulated too little mass to sustain hydrogen fusion and have been cooling ever since. Cold, old, rogue planets drifting in the dark between stars, expelled from their home systems by gravitational encounters over billions of years of dynamical evolution. Dark matter structures still threading through the voids and filaments of the cosmic web, gravitating and interacting with ordinary matter gravitationally, but invisible to light. If protons are unstable, as some extensions of the Standard Model predict, though this has not been confirmed experimentally, with proton lifetimes constrained to greater than about 10 to the 34 years by direct experiment, then during the degenerate era, the matter in white dwarfs and neutron stars will slowly decay. The stellar remnants will dissolve over timescales of roughly 10 to the 37 years, leaving a diffuse wash of particles and radiation. Even if protons are stable, gravitational dynamics will eventually disrupt the structure of galaxies and their remnants through two-body gravitational interactions that slowly exchange energy between objects, over timescales of about 10 to the 19 years for stellar mass objects to be ejected from their galaxies. After the degenerate era, the universe enters the black hole era. Nothing remains but black holes of various masses, scattered through an increasingly vast and cold and dark cosmos. These black holes are not permanent. Stephen Hawking calculated in 1974 that quantum effects near a black hole's event horizon cause the black hole to emit radiation and slowly lose mass, a process now called Hawking radiation. The process is extraordinarily slow. A black hole with the mass of the Sun would take approximately 2 times 10 to the 67 years to evaporate completely. A supermassive black hole with a billion solar masses would take roughly 10 to the 100 years. But given enough time, it happens. Every black hole in the universe eventually evaporates. After roughly 10 to the 100 years, the last black hole is gone. The universe contains nothing but the residue, a sparse bath of photons, neutrinos, electrons, positrons, and other stable particles, spread through an enormous volume at a temperature indistinguishable from absolute zero. This is the dark era. This is the heat death. The universe has reached its maximum entropy state, or as close to it as it can reach with the residual quantum fluctuations of the de Sitter background. Now ask, how long does the dark era last? In a universe with a positive cosmological constant, the expansion continues. The temperature is not exactly zero, because de Sitter space has the Gibbons-Hawking temperature, a tiny but non-zero temperature arising from quantum effects at the cosmic horizon. The universe is in a state of near-thermal equilibrium with tiny fluctuations. It persists like this indefinitely, forever, without end. There is no moment at which the dark era concludes. There is no final state that the universe reaches and then stops. It goes on, cold and dark and quiet, fluctuating at the quantum level, but doing nothing macroscopically interesting, for a duration that has no upper bound, not for a Google years, not for a Googleplex years, not for any finite number of years, forever. And in that forever, the Boltzmann brain problem reemerges. Given infinite time in a de Sitter background with a finite temperature, quantum fluctuations will spontaneously produce, with certainty, any physical structure that is thermodynamically possible, including observers. The question of whether this actually happens depends on the quantum gravity description of de Sitter space, which is not yet fully understood, and some researchers argue that the de Sitter vacuum does not actually fluctuate in the relevant way. But the problem sits there, at the end of the universe's story, unsettled. If the Big Rip occurs instead, the heat death is preempted. The accelerating expansion driven by phantom dark energy grows without limit, eventually overwhelming all bound structures. In the final moments of a Big Rip universe, the story is different. Galaxy clusters are pulled apart, perhaps 100 million years before the end. Individual galaxies disrupt perhaps 65 million years before the end. The Milky Way and Andromeda, which are expected to merge in about 5 billion years from now and form a combined elliptical galaxy, would be torn apart roughly 100 million years before the Big Rip. The solar system is disrupted about 3 months before the end. The Earth is ripped apart about 30 minutes before the end. Atoms are destroyed about 10 to the minus 19 seconds before the end, and then the singularity. The Big Rip is, in a sense, a cleaner ending than the heat death. It has a definite time. It is a specific event. It happens at a specific moment in the universe's history, and then there is nothing. No de Sitter fluctuations, no Boltzmann brains, no lingering warmth. Just a final singularity, and then the absence of space-time itself. Whether the universe ends in the gradual, quiet heat death of a de Sitter forever, or in the violent finality of the Big Rip, or in some scenario not yet conceived, the scale of the ending is what should stop you. Even in the more conservative heat death scenario, the universe lasts for durations that make 13.8 billion years, the entire history of the cosmos to date, look like the first flicker of an eye. The universe we live in now, with its active stars and spiraling galaxies and warm rocky planets, is the universe at its most organized and dynamic. It is early morning. Everything that follows is a long, slow afternoon, and then a night that lasts forever. We happen to arise in the morning. Something about that deserves to be noted. Part 10. The Reason. Everything we have covered arrives at a question. The question in the title. The universe is infinite for a reason. What is the reason? There are honest and honest answers. The honest scientific answer is, we do not fully know. The flatness of the universe, which implies infinite extent in the simplest model, is explained mechanically by inflation. Inflation stretched the initial geometry to flatness. The eternal continuation of inflation, beyond our observable bubble, produces an infinite number of pocket universes. The logic chains from observation to inflation to eternal inflation to infinite universes. And it is a chain with strong links at the beginning and more speculative ones toward the end. But why did inflation happen at all? Why did the inflaton field exist with the properties it has? Why did the initial state of the universe prior to inflation permit inflation to begin? These questions currently have no answers. The theory of inflation is enormously successful as a description of what happened. As an explanation of why it happened, it is silent. It takes a given initial state and tells you what emerges. It does not tell you where the initial state came from or why the universe had that state rather than some other. There are speculative proposals. The Hartle-Hawking no-boundary proposal in quantum cosmology attempts to describe the quantum state of the universe itself as a wave function without an initial boundary, a universe that emerges from a quantum geometry with no singular beginning. In this picture, the initial conditions are not imposed from outside, but are determined by the quantum mechanics of the universe's own wave function. If the proposal is correct, asking what caused the Big Bang is like asking what is north of the North Pole. There is no answer, not because the question is too hard, but because it is malformed. The universe is its own cause in a quantum gravitational sense. Whether this proposal is correct is unknown. It is mathematically interesting and philosophically compelling, but not yet empirically testable in any direct way. What we are left with is a situation where the infinite extent of the universe follows from the physics of inflation. The physics of inflation is supported by extraordinary evidence, and the origin of the inflationary initial conditions is genuinely unknown. The infinite universe is real, most likely. The reason it is infinite, in any ultimate sense, is not established. But there is a different way to read the question, not what mechanism produced the infinite universe, but what does living in an infinite universe mean? What is the significance of the infinity for everything within it? And here, the answers are more definite, even if not more comfortable. An infinite universe means that every possible physical configuration of matter exists, somewhere, including you, including every version of every decision you have ever faced, including every life you could have lived and did not, including versions of this moment in which things are going differently, in which you are somewhere else, in which the video you are watching is slightly different, or in which you are not watching at all. All of those configurations of matter exist in the infinite space beyond the horizon, as physically real as this one. Your uniqueness is local. Within the observable universe, you are almost certainly the only instance of your specific configuration. The observable universe is rich and vast and contains enough matter to produce complexity, but not so much that complexity is infinitely repeated within it. You are singular here. This moment is singular here, in the sense that it does not repeat within the space we can observe. But here is not everything. The universe is not asking for your comfort. It is not organized around making you feel special in a cosmic sense. It is organized around the laws of physics, and those laws, operating in infinite space, produce infinite repetition of every finite configuration. The fact that you feel singular and unrepeatable is a fact about the observable universe, a fact about the 93 billion light-year bubble that is all any human has ever seen or will see. It is a local fact, true locally, bounded locally. The terrifying part is not really the copies. You can intellectually acknowledge them, and they need not disturb your day. They are unreachably far away. They will never interact with you. Your choices still matter. Your life still has the meaning it has. Your relationships and your work and your experiences are still fully real within the causal structure of your local universe. The copies do not diminish any of that. The genuinely unsettling part is what the infinite universe says about the status of laws and origins, about why things are the way they are rather than some other way, about whether there is a reason for the specific constants, the specific flatness, the specific symmetries that made this particular universe the kind of place where stars and planets and minds could arise. If the multiverse is real, if eternal inflation produces all possible pocket universes with all possible physics, then the specific features of our universe are not unique and universal truths. They are local accidents. They are the physics of this bubble. Other bubbles have different physics. Our cosmological constant is one of an infinite number of cosmological constants spread across the infinite multiverse. Our strong nuclear force coupling is one of an enormous landscape of possible values. Our three large spatial dimensions are one configuration among many. This means that physics, as we know it, is a local science. The laws we discover by experiment are the laws of this bubble. They may not apply elsewhere. There may be no universal laws in the sense of laws that hold everywhere, because there is no single physics that holds everywhere. There is our physics, and there is the physics of every other pocket universe, and those physics are different, and there is no metaphysics that all of them share, except perhaps the most abstract mathematical structures. This is either the most liberating or the most destabilizing perspective in all of science, depending on your temperament. It liberates you from the burden of explaining why the constants have the values they do. They have the values they do because every possible value exists somewhere, and we find ourselves in a bubble where the values permit us. The explanation is anthropic. The mystery dissolves. But it takes something away, too. It takes away the sense that discovering the laws of physics is discovering something universal and permanent and true, not just about this region of space and time, but about reality itself. In the multiverse picture, the laws of our universe are more like local regulations than universal principles. True here, not necessarily true there. Not the deep structure of reality, but the specific rules of one bubble among infinite bubbles. And that is where the infinite universe becomes genuinely, quietly terrifying. Not in the sense of immediate danger, not in the sense of any threat to your life or your daily existence. Terrifying in the deeper sense that it removes the ground from under the most fundamental question science can ask. Why is the universe the way it is? In a multiverse, the answer is that the universe is not the way it is in any universal sense. It is the way it is here, there. It is different. The question dissolves, and the dissolution is not satisfying, it is disorienting, because the question seemed important and now it turns out to be malformed, like asking what is north of the North Pole. And yet, right here, right now, in this specific bubble of cosmic history, in the first morning of a universe that will persist for trillions and trillions of years, something extraordinary is happening. Matter has organized itself into entities capable of perceiving their own smallness. Stars are being cataloged by the fusions that built the atoms, composing the observers doing the cataloging. A universe has, in some tiny corner of its early history, become aware of itself and begun to wonder why it exists. That does not happen everywhere. In the sterile, dark universes with the wrong constants, there is nobody to wonder. In the universes that recollapsed in an instant, there is no history to wonder about. In the universes that expanded so rapidly they never formed structure, there are no observers to ask questions. This one produced wonder. For whatever reason, by whatever mechanism, in this one bubble out of infinite bubbles, the constants lined up, the geometry was flat, inflation happened, structure formed, stars ignited, planets cooled, chemistry got interesting, and eventually, after an improbable cascade of events covering 13.8 billion years and an incomprehensible range of scales from the quantum to the cosmic, something with an inner life looked up at the stars and started asking questions. The universe did not do this for us. It does not know we are here. It does not care about the questions we ask. But the questions are being asked, and the answers we have found so far, partial and strange and vertiginous as they are, constitute the most honest description of existence that any part of the cosmos has ever produced. The universe is infinite for a reason. We do not know the reason. We may never know the reason. But we are here, in this finite moment, in this finite observable bubble, asking. And that asking, as small and local and impermanent as it is, seems to matter, at least from the inside. From the outside, if the infinite universe even has an outside, it is one more pattern in an infinite set of patterns, repeating somewhere an infinite number of times, and persisting for a duration that has no end. Both of those things are true simultaneously. Local significance and cosmic insignificance are not in contradiction. They operate at different scales. and the universe is vast enough to contain both. If this video left you with something to think about, hit the like button and subscribe so you do not miss what comes next. Drop your thoughts in the comments below. Tell me where you are watching from and what time it is. Tell me which part of this sits hardest with you. Tell me what you are still thinking about as the video ends. Because these are the questions worth thinking about. Not because they are comfortable, but because they are real. And real questions deserve real attention, no matter how far beyond comfortable they go. End of script. Extended deep dive. What infinite actually breaks? There is a mathematician's definition of infinity and a physicist's problem with it, and they are not quite the same thing. The mathematician defines infinity as a set without an upper bound, a collection of objects that you can always add one more to. The mathematician knows that infinities come in different sizes, a fact that was established by Georg Cantor in the 19th century and remains one of the most counterintuitive results in all of mathematics. The integers are infinite, the real numbers are also infinite, but Cantor proved that the infinity of the real numbers is strictly larger than the infinity of the integers. There are more real numbers between 0 and 1 than there are integers from 1 to infinity. Some infinities are literally bigger than other infinities. This is not just an abstract curiosity. It has direct implications for how you reason about an infinite universe, because not all infinite things are the same, and applying the wrong intuitions from finite reasoning to infinite settings leads to conclusions that are either wrong or incoherent. Here is a classic example of how infinity breaks ordinary reasoning. In a hotel with infinite rooms, all currently occupied, you can always accommodate a new guest. Move the guest in room 1 to room 2, the guest in room 2 to room 3, the guest in room 3 to room 4, and so on. Every guest shifts one room along, and the process never terminates because there are always more rooms. Room 1 is now empty for the new guest. The hotel with an infinite number of rooms and a full occupancy can still accommodate infinitely many new guests. This is Hilbert's Hotel, and it illustrates that the rules of finite arithmetic do not apply to infinite sets. In the infinite hotel, full plus 1 is still full, and full plus infinity is also still full, in the sense that there is a way to accommodate every guest. Apply this to the infinite universe, and you get results that sound paradoxical but are correct. If the universe contains infinitely many copies of you, and those copies each make a different decision at some branch point in their lives, the number of copies making decision A is infinite, and the number making decision B is also infinite. Both are full infinities. There are not more copies making one choice than the other. There are infinitely many making each. The concepts of more and less do not apply cleanly to infinite sets in the way they apply to finite ones. You cannot say that most copies made one choice, or that the majority had one experience. Those concepts require countability and comparison that infinite sets do not straightforwardly permit. This is the measure problem that haunts multiverse cosmology. In an infinite universe with infinite copies of everything, how do you define probability? How do you say that something is typical, or rare, or expected? The usual probabilistic statement is that an event has probability p if, in a long run of trials, it occurs with a fraction p of the time. But in an infinite setting, every event that has non-zero probability occurs infinitely many times, and so does every other event with non-zero probability. The fractions of infinities are not straightforwardly defined without additional mathematical structure, called a measure, that tells you how to weight different parts of the infinite space. In the context of eternal inflation, the measure problem is acute. There are infinitely many pocket universes, each producing observers. Among all the observers in the eternal multiverse, what fraction observe a particular feature of their universe, say a particular value of the cosmological constant, or a particular density of matter? This question seems simple, but answering it requires comparing infinities, and without a well-defined measure, the comparison is ambiguous. Different ways of defining the measure give different answers, sometimes wildly different answers, and there is no agreed principle for choosing the right measure. This is not a technical detail. It is a fundamental problem with extracting predictions from multiverse theories. If the theory does not have a well-defined measure, it cannot make definite probabilistic predictions, which means it cannot be falsified, which means it fails to meet one of the basic criteria for scientific theories. The measure problem is one of the main reasons that many physicists remain skeptical of multiverse theories, even when they accept the inflationary cosmology that generates them. Guth himself has described this as one of the central unsolved problems in inflationary cosmology. He described the awkwardness of calculating probabilities in eternally inflating spacetimes as the Youngness paradox, one version of which produces the absurd prediction that randomly selected observers in an eternally inflating universe should almost certainly be newborns, because pocket universes are produced at an exponentially increasing rate, and the most recently produced ones are always the most numerous. This is obviously not what we observe, which indicates that the naive probability calculation is wrong, but getting the right probability calculation requires a measure that nobody has definitively established. The infinite universe is real, or at least very probably real based on the physics, but our tools for reasoning about probability and typicality in infinite settings are inadequate. We can describe what is possible in an infinite universe. We struggle to describe what is typical or expected. Extended deep dive, the light that will never arrive. There is another layer to the story of what the infinite universe means in practice. Not just the copies and the physics, but the experience of living within it. The experience of being a finite, local observer in an infinite, global cosmos. Right now, as you are reading or watching this, photons of light are arriving at Earth from billions of sources. Every one of those photons carries information about where it came from and when. The light from the Sun takes about 8 minutes to arrive. The light from Proxima Centauri, the nearest star, takes about 4 years. The light from the Andromeda Galaxy, which you can just barely see with the naked eye on a clear dark night as a faint smear of light, took about 2.5 million years to arrive. What you see when you look at Andromeda is not Andromeda now, but Andromeda as it was 2.5 million years ago, before the first members of the genus Homo walked the African savanna. The light from the most distant galaxies ever observed by the James Webb Space Telescope took about 13.5 billion years to arrive. Those galaxies existed only a few 100 million years after the Big Bang. They have had 13.5 billion years to evolve and change since that light left them. They may no longer resemble the objects whose ancient light we are receiving. They may have merged with other galaxies, changed their star-forming properties dramatically, grown to many times their original size. We cannot know what they look like now, because the light showing us now has not arrived yet. This delay between emission and reception is the fundamental barrier to observational astronomy. Every telescope is a time machine looking backward. The farther you look, the further back in time you see. And the cosmic microwave background, the radiation filling the sky from the epoch of recombination 380,000 years after the Big Bang, is the oldest light we can see. It is a wall of light from which no older photons can reach us. Before recombination, the universe was opaque. No photons from that earlier era have made it through to our telescopes because they were continuously absorbed and re-emitted in the hot, dense plasma, never able to free stream across the universe. The CMB is the earliest snapshot we will ever have. But beyond the CMB, the universe continues. The Big Bang was not a local event. It was not an explosion at a point in pre-existing space. It was the beginning of space and time themselves. Every point in the universe traces back to the same hot, dense early state. The universe did not expand from a single location into surrounding empty space. Space itself expanded, and it expanded everywhere simultaneously. The CMB you receive from the northern sky and the CMB you receive from the southern sky both came from regions of the early universe that were about 42 million light-years from our location at the time they emitted that radiation. They are now about 46 billion light-years from us in opposite directions. We cannot see anything older, but there is something older in every direction, in the sense that the universe continued before recombination. We just cannot receive information from it. Now consider what is happening at the edge of our observable universe right now. The most distant galaxies we can observe are, as mentioned, currently about 46 billion light-years away. Those galaxies are still there. They are still emitting light. That light is traveling toward us right now. It will not arrive for tens of billions of years. The universe will be dramatically different by the time it does. Many of those distant galaxies will have receded beyond our event horizon by then, carried away by the accelerating expansion, meaning their future light will never reach us, even if we wait forever. The light emitted right now from galaxies near the edge of our observable universe is in a race between its travel toward us and the expansion that is carrying its source ever farther away. For galaxies beyond a certain distance, the race is already lost. The expansion is already faster than light, in the sense that the galaxies are moving away from us faster than light can close the gap. This is not a violation of special relativity. Special relativity prohibits objects moving through space faster than light. It says nothing about the rate at which space itself can expand. Space can expand at any rate. The recession velocities of distant galaxies, calculated as the rate of change of their distance from us, can and do exceed the speed of light for sufficiently distant objects. Light from those objects can still reach us if it was emitted in the past when they were close enough, but light emitted from them now, with the expansion at its current rate, will never catch us. We are moving away from each other faster than light can travel. The future observable universe is therefore smaller than the current one. Galaxies that we can see today will eventually recede beyond the event horizon, and their future light will never arrive. The night sky of the far future will be progressively darker, not because the universe is collapsing, but because it is expanding, carrying away the sources of light into regions from which no information will ever return. In tens of billions of years, the local group will merge into a single, large elliptical galaxy, Milkomeda, the combined remnant of the Milky Way and Andromeda and their satellite galaxies. This combined galaxy will be the only galaxy visible in the night sky. Everything else will have been carried beyond the horizon. A civilization in Milkomeda, then, lacking any historical records of the current epoch, would have no observational evidence that other galaxies ever existed. They would look out at the night sky, see only their own galaxy, and conclude that the universe consisted of a single island of stars in infinite void. They would have no way to know about the 2 trillion galaxies that filled the observable universe in the early epoch of cosmic history, because that information would no longer be accessible. It would have been carried away by the expansion. This is one of the most profound implications of the accelerating expansion. We exist in a cosmologically privileged moment, an early epoch when the universe is still young enough and the expansion still slow enough that the observational record of the universe's history is rich and accessible. The CMB still fills the sky. The distant galaxies are still visible. The large-scale structure of the cosmic web is still measurable. Future civilizations, if they exist, will have less access to this information than we do. The universe is, in a sense, hiding its own history from future observers by expanding away the evidence. We have the information now. The question is whether we know how to use it. Extended deep dive, the silence of the other rooms. The copies of you in the infinite universe, the exact duplicates Tegmark calculated, the near copies diverging by quantum events, the versions living different lives in different configurations of the same physics, will never contact you, not because of any failure of technology, not because of any philosophical barrier, because of causality. The causal structure of spacetime is absolute. No signal travels faster than light. No information can traverse a distance that requires more time than the information has been available. The light speed limit is not a speed limit on objects moving through space that might someday be circumvented. It is a fundamental property of the relationship between space and time in the physics of our universe. Nothing propagates causally faster than light, and everything propagates causally at most as fast as light. Your nearest exact copy is approximately 10 to the power of 10 to the power of 29 meters away. Light crosses 1 meter in about 3 nanoseconds. To cross 10 to the 29 meters, light would take about 10 to the 21 years. That is 1,000,000 times longer than the current age of the universe. And your nearest copy is not 10 to the 29 meters away, but 10 to the 10 to the 29 meters away, which is the 10 to the 29 power times farther than that. The transit time for any causal signal between you and your copy is a number that has no name and no human analog. The heat death of the universe will have occurred, the last black hole will have evaporated, and the dark era will have persisted for inconceivable eons before any signal you sent today could arrive. You and your copy are causally disconnected. You are as isolated from each other as if you were in separate universes, even though you are in the same universe. The infinity of space creates effective isolation, as complete as any wall. This means that the copies are real, but irrelevant to your life in the most practical sense. They exist, they are you, or versions of you, or near versions of you. But they cannot help you, cannot harm you, cannot communicate with you, cannot observe you, cannot affect any decision you make. Your choices are made in your local causal bubble, and they matter locally. The infinite copies living their infinite versions of your life are no more accessible to you than the people who lived before your birth. And yet knowing they are there changes something. Not in any practical sense, but in the sense of how you hold the concept of your own existence. The isolation is real. The causal disconnection is absolute. But the knowledge that the isolation exists within a structure of infinite repetition creates a different relationship with the idea of singularity. You are not the only you, but you are the only you that you can interact with, the only you that you can be, the only you who can make the choices in front of you, in this moment, in this life. The singularity is real at the scale at which you actually operate. The repetition is real at scales you cannot reach. Both are true. They are not in contradiction. They are simply facts at different scales, and the universe is large enough to contain facts at radically different scales that do not conflict even when they seem to. Extended deep dive. Why inflation is almost certainly real. A question that deserves more time is how confident we actually are in inflation. It is one thing to say that inflation explains the flatness and the horizon problem. It is another thing to say that inflation actually happened. The history of physics contains many elegant theoretical explanations that turned out to be wrong. The confidence in inflation comes from several converging lines of evidence, some of which are extraordinarily precise. The first is the flatness. We measured the curvature of the universe to within 0.4%, and it is flat. Inflation predicts flatness. The agreement is striking. The second is the spectrum of fluctuations in the cosmic microwave background. Inflation predicts that quantum fluctuations in the inflaton field will produce a spectrum of density perturbations with a very specific mathematical shape, a nearly scale-invariant power spectrum with a slight tilt towards slightly more power at large scales than small scales. The parameter describing the tilt is called the spectral index, denoted NS, and the simplest inflationary models predict it should be close to but slightly less than 1. The Planck satellite measured this spectral index to be approximately 0.965, precisely in the range predicted by inflation and inconsistent with a perfectly scale-invariant spectrum. The third is the absence of certain exotic relics. Grand unified theories of particle physics predict that at the enormous energies of the very early universe, magnetic monopoles, exotic particles with a single magnetic pole rather than the two poles of ordinary magnets, should have been produced copiously. We have never detected a single magnetic monopole. Inflation solves this by diluting the monopole density to essentially zero, stretching the volume of space by such an enormous factor that the monopoles produced before inflation are spread so thin that you would need to search an absurdly large volume to find even one. The fourth, which would be the most direct evidence if confirmed, is primordial gravitational waves. Inflation should produce a background of gravitational waves, ripples in spacetime generated by the same quantum processes that produce the density fluctuations. These gravitational waves would leave a specific imprint in the polarization pattern of the cosmic microwave background, a swirling polarization pattern called B-mode polarization that would not be produced by ordinary scalar fluctuations. Several experiments, most notably B-ICEP-2 and the Keck array and the CMB-S4 experiment currently being built, are searching for this B-mode signal. It has not been definitively detected yet, but the search is ongoing, and a detection would be one of the most significant confirmations of inflationary theory ever obtained. The cumulative weight of the evidence is substantial. Inflation is not just a theoretical convenience. It is a model that makes specific, quantitative predictions about measurable properties of the universe, and the measurements so far are consistent with those predictions to a degree that would be very difficult to explain without something like inflation. Whether inflation is exactly the form proposed by Guth or requires modifications is still under investigation. There are many specific inflationary models, each with slightly different predictions, and the precision of current measurements is not yet sufficient to definitively distinguish between them. But the broad picture of a period of exponential expansion in the very early universe, with quantum fluctuations seeding large-scale structure, is supported by the data. And if inflation happened, and if the simplest inflationary models are anywhere near correct, then eternal inflation almost certainly happened. The eternal nature of inflation is not an add-on, but a generic consequence of the quantum dynamics of the inflaton field. It follows from the same physics that produces the flatness and the spectrum of fluctuations. If you accept inflation on the basis of the evidence, you are accepting, along with it, a universe that produces infinitely many pocket universes and extends infinitely beyond our cosmic horizon. The infinity is not a separate hypothesis. It is part of the package. Extended deep dive, the deep strangeness of fine-tuning. The fine-tuning problem is worth lingering over because it is easy to state and difficult to feel the full force of. The statement is, the physical constants of the universe are set to values that permit complex structure to exist, and modest changes to those values would produce a universe incapable of forming atoms, stars, or life. The difficult part is appreciating how strange this is. Begin with carbon. Carbon is the backbone of organic chemistry, the element on which all known life is built. Carbon is special because it can form 4 simultaneous chemical bonds, allowing it to connect with 4 other atoms in a stable molecule. This tetravalent bonding is what makes the enormous variety of organic molecules possible, from simple hydrocarbons to the enormously complex proteins, DNA, and enzymes that constitute living organisms. Without carbon and its bonding flexibility, the chemistry of life as we know it could not exist. Carbon is made in stars. The process that produces carbon was discovered by Fred Hoyle in the 1950s, and it involves a nuclear resonance that Hoyle predicted must exist before it was experimentally confirmed, one of the most dramatic theoretical predictions in the history of astrophysics. Carbon is produced when 3 helium nuclei fuse together, in a process called the triple alpha process, because helium nuclei are sometimes called alpha particles. The problem with this process is that it requires 3 helium nuclei to come together essentially simultaneously, which is very unlikely because 3-body collisions are rare. The way nature solves this is through a nuclear resonance, an excited state of carbon-12 that sits at almost exactly the right energy to be populated by the collision of beryllium-8 and helium-4, which is a more likely 2-body process. Because of this resonance, carbon is produced efficiently enough in stellar cores to be the abundant element we observe. Here is the fine-tuning part. The energy of this resonance in carbon-12 is 7.656 MeV. If it were just a few % different, the resonance would not be accessible at the temperatures inside stars, and carbon would not be produced in significant quantities. No carbon means no organic chemistry means no carbon-based life. The resonance energy depends on the precise values of the strong nuclear force and the electromagnetic force. If either of those constants were slightly different, the resonance energy would shift enough to eliminate carbon production. Fred Hoyle himself, a committed atheist and materialist, found this so striking that he wrote, famously, that a common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics as well as chemistry and biology. He was not making a religious argument. He was expressing genuine astonishment at the precision required. The carbon resonance is one example. There are dozens of others. The mass difference between the proton and the neutron is about 1.3 MeV. If the neutron were much lighter, it would decay more slowly and hydrogen would be converted almost entirely to helium in the early universe. leaving no fuel for long-lived hydrogen-burning stars. If the neutron were much heavier, it would decay more quickly, and most of the universe's hydrogen would be ordinary protons with very few neutrons left to make heavier elements. The strength of the weak nuclear force determines the rate at which heavy nuclei decay and the rate at which certain fusion processes proceed in stellar cores. If the weak force were stronger, neutrinos from supernovae would be trapped inside the collapsing stellar core and would not be able to blow off the outer layers in the supernova explosion. Without supernova explosions, the heavy elements synthesized in stellar cores, the carbon, oxygen, iron, and all the others, would remain trapped inside the dead stellar remnants. The universe would have no mechanism for spreading heavy elements into interstellar space, where they can be incorporated into new planetary systems. No heavy elements outside of stellar cores means no rocky planets, no oceans, no chemistry, no life. Each of these examples is a case where the physics of our universe sits at a value that makes something important possible, a value that was not arrived at by any currently understood selection mechanism, not demanded by any currently understood deep principle, but that happens to work, in a universe where the alternatives, the vast majority of other possible values, would produce a cosmos of staggering sterility. Some physicists argue that these examples reflect our anthropocentric bias, that we notice the tunings that matter for our existence because we are here, and we fail to notice the vast space of physical possibilities where no such tuning is required, because nobody is there to notice. This is the anthropic point. It is logically valid, but it does not explain why there is any life-permitting configuration at all, only why we find ourselves in one rather than in one of the sterile alternatives. Others argue that the fine-tuning may be illusory, that a deeper theory will show the constants are constrained to their observed values by some symmetry or self-consistency requirement we do not yet understand. This is also possible, but it is an aspiration, not an achievement. The deeper theory has not yet been found. And others, including some of the most prominent physicists working today, take the multiverse seriously, precisely because it offers the only framework in which fine-tuning has a naturalistic explanation without requiring a new physical principle. In an infinite multiverse, with all possible physics, life-permitting physics is not surprising. It is expected. We find ourselves in a universe that permits our existence because no other kind could contain us. Whether this explanation is satisfying, whether it counts as a genuine scientific explanation, is a question that the physics community has not resolved. But the fine-tuning is real, and the stakes of the question are as high as any in science. Extended deep dive, being small in something infinite. There is a psychological dimension to the infinite universe that is worth acknowledging, not because it changes the physics, but because the physics changes us when we really take it in. The human brain evolved to navigate a social landscape, a physical environment, and a temporal horizon that are all finite and relatively local. The brain is exquisitely tuned to the scale of the savanna and the clan and the season. It is not tuned to process the infinite. When you genuinely try to feel what infinite space means, what it means for there to be no end to the expanse of matter and energy and time, the brain tends to produce one of a few standard responses. Some people feel vertigo, a sense of groundlessness, like standing at the edge of something with no bottom. Some people feel a kind of desperate urgency, as if the infinite somehow threatens the local meaning of their lives. Some people feel, paradoxically, a deep calm, a release from the burden of cosmic significance, because if everything is infinite and everything repeats, then nothing needs to carry the weight of being unique to be real. None of these responses is wrong. They are all natural responses to a genuine confrontation with scale. And the question of which response is the right one, whether the infinite universe is a source of terror or comfort or equanimity, is not a physics question. It is a question about how you want to live in relation to what you know. The physics does not tell you how to feel. It tells you what is true, or at least what the current best evidence suggests is true. And what it suggests is that you exist in a universe that is almost certainly infinite, that contains infinite copies of you and infinite variations on your life, that was produced by a mechanism that generates infinite universes, that is governed by constants whose values are tuned in ways nobody fully explains, that is expanding and cooling toward a heat death or a big rip that will come billions of years from now, and that within all of this enormity, in the first few billion years of the universe's long life, matter organized itself here into systems capable of understanding their own place in the structure. That last part is not nothing. It is, in a sense, the most remarkable thing in the entire story. Not because it is cosmically significant in the sense of the universe caring about it, but because it happened. Out of the specific constants, and the specific geometry, and the specific history of this specific bubble, something emerged that can ask why. Something emerged that can measure the CMB, and map the cosmic web, and calculate the distance to its nearest copy, and sit with the question of why the constants permit its existence. The infinite universe produced, in one small corner, in one early moment, a local improbability so profound that no probability calculation adequately describes it. Not a Boltzmann brain, a random fluctuation. A causally evolved observer, the product of 13.8 billion years of physics working on the initial conditions of a single inflationary pocket, producing galaxies, producing stars, producing planets, producing chemistry, producing biology, producing neurology, producing something that can read these words and understand what they mean. In an infinite universe, this also happens infinitely many times. There are infinitely many observers in infinitely many pockets. This one is not special in the cosmic inventory, but it is the one you are in. And from the inside, from the only perspective available to any observer at any time, that is everything. The terror and the wonder are the same phenomenon viewed from different angles. The infinite universe does not care about you. The infinite universe also happened to make you. Both are true. Sit with that. End of script. Extended deep dive. The observable universe as a prison and a gift. There is a duality at the heart of the cosmic horizon that deserves its own exploration. The horizon is, in one sense, a prison. It bounds everything you can ever directly observe. It sets a hard ceiling on the information available to any observer anywhere. You cannot receive information from beyond it. You cannot send a signal to beyond it and receive a response. You are causal inmates of a bubble of space-time, and the walls of that bubble, though they move with you as the universe ages, are walls nonetheless. Everything you can ever know about the universe by direct observation is contained within a sphere of 46.5 billion light-years radius, and that sphere is an infinitesimal fraction of what almost certainly exists. But the horizon is also a gift. Because it is finite, the observable universe is comprehensible. It is something you can attempt to catalog, to measure, to map, to understand. It has a total mass-energy content that can in principle be counted. It has a finite number of galaxies, a finite number of stars, a finite number of planets, a finite number of particles. All of those numbers are enormous beyond any everyday comparison. But they are finite, and finite things can in principle be known. If the entire infinite universe were somehow accessible to observation, it would be impossible to map or understand or comprehend in any practical sense. The information content of an infinite universe is literally infinite, and no finite mind or instrument could process it. The cosmic horizon, by limiting what we see to a finite region, makes physics possible. It makes science possible. It constrains the question to something that, however difficult, has a finite set of answers. The relationship between the finite observable and the infinite total is one of the most profound aspects of the human scientific situation. We are finite observers, with finite instruments, studying a locally finite region of an infinite cosmos. The physics we discover is the physics of our bubble, and we have no direct access to whether or how it differs in other bubbles. But the physics of our bubble, studied with the precision that modern instruments allow, tells us about inflation and flatness and the cosmic microwave background and the large-scale structure of the universe. And from these local observations, we infer the existence and the probable nature of the infinite beyond. It is, in a sense, the most extraordinary extrapolation in the history of human knowledge. from measurements made within a 93 billion light-year bubble, using instruments that can only probe a small fraction of that bubble in any detail, we have inferred that the bubble is embedded in an infinite universe, and have constrained the nature of that infinite universe with genuine quantitative precision. The ancient human intuition, common to many cultures and philosophies, that we are small and the cosmos is vast, turns out to have been not merely a spiritual insight, but a precise scientific statement. We are small, the cosmos is vast, vaster than the word vast can convey, vaster than the concept of vast is designed to handle, and we, from our small corner, have managed to work out most of this. That is perhaps the most remarkable thing about this whole story. Not the infinity of the universe, which is vast and impersonal and indifferent, but the fact that within the infinity, in one small and probably unremarkable bubble, in the first few billion years of that bubble's history, collections of matter evolved to the point where they could determine that the universe is infinite, that they could measure the flatness to 0.4%, that they could calculate the distance to their nearest copy, and discover that their existence repeats an infinite number of times in the spaces beyond their sight. The universe did not intend any of this, but it happened anyway. Extended Deep Dive. The question behind the question. Every major question in cosmology eventually arrives at a boundary. Not the cosmic horizon, but a conceptual boundary. The point where the current theories run out of explanatory power, and the only honest answer is that we do not know. Why did the Big Bang happen? We do not know. Current physics can describe the universe from a fraction of a second after the Big Bang forward, with increasing precision as the understanding of early universe particle physics improves. But the moment of the Big Bang itself, the Planck epoch, the first 10 to the minus 43 seconds, is currently beyond the reach of any theory we have, because it requires a quantum theory of gravity that does not yet exist. General relativity and quantum mechanics, our two most successful physical theories, are mutually incompatible at the energy scales of the Planck epoch. We need a unified theory to describe what happened then, and we do not have one. Why does inflation end in a specific way in our bubble? We do not know. The potential energy curve of the inflaton field, which determines when and how inflation ends, is not derivable from any deeper principle in the current theory. It is a phenomenological model that fits the observations, but is not derived from anything more fundamental. Why is the cosmological constant the value it is? We do not know. The worst prediction in physics remains wrong, and the mechanism that sets the observed value remains unknown. Why are there 3 large spatial dimensions? We do not know. String theory requires 10 or 11 dimensions, with the extra dimensions compactified to small sizes. Why 3 of those dimensions are large and the others are small is not yet derived from any first principle. Why does anything exist rather than nothing? We do not know. This is the ultimate question behind all the others. And it may be the question that physics is structurally incapable of answering, because any physical explanation invokes existing physical laws and entities, and the question being asked is why those laws and entities exist at all rather than nothing. Quantum cosmology, in its most developed forms, tries to address this by treating the universe as a quantum system and asking about the quantum probability of a universe like ours arising from nothing. But even this approach requires the existence of quantum mechanical laws, and the question of why those laws exist rather than nothing is pushed back but not eliminated. Every physical explanation starts with some given structure, some background of physical law and mathematical reality, and the question of why that background exists is always waiting one step further back. This is not a failure of physics. It may simply be the nature of questions. Every chain of explanations must start somewhere. The starting point is not explained by the chain. It is the ground on which the chain rests. Whether that ground has an explanation, whether there is a metaphysics that explains why physics is the way it is a question that current science does not address and may not be able to address. The infinite universe, for all its strangeness and all its implications, is part of the same chain of physical explanation. It follows from inflation. Inflation follows from the quantum dynamics of the inflaton field. The inflaton field exists within a universe with specific initial conditions. The specific initial conditions are not explained by the chain. They are the starting point of the chain. At the bottom of the universe, under all the physics and all the math, and all the beautiful interlocking explanations, there is something that physics simply takes as given: a ground state, an initial condition, a set of mathematical structures that exist and that produce, by their operation over 13.8 billion years, a cosmos that includes within it something capable of asking why they exist. The question has no current answer, but the fact that it is being asked, here, now, by something that the universe built out of atoms and time, is, in its own quiet way, the most extraordinary fact in the whole infinite story. End of script. Extended deep dive: the scale problem in human minds. There is something the infinite universe does to ordinary language that is worth being explicit about. Language evolved to describe finite things. Words like big, huge, vast, enormous were shaped by the experience of things that are large by human standards, but tiny by cosmic ones. We can extend these words to cosmic scales through metaphor and comparison, but there is a point at which the extension stops carrying any experiential weight and becomes merely a string of symbols with a technical definition attached. The observable universe contains roughly 2 times 10 to the 23 stars. Write that number out. It is approximately 200 million Milky Way, 200 sextillion. If you laid those stars end to end, in a line, spaced at the average distance between stars in the Milky Way, about 5 light-years apart, the line would extend for 1,000,000 trillion light-years, vastly farther than the observable universe itself. The number is not just large. It is large in a way that comparison to human-scale things breaks down immediately. Carl Sagan famously observed that there are more stars in the observable universe than grains of sand on all the beaches of the Earth. This is a true comparison. It is also almost immediately useless as an aid to genuine comprehension, because while you can conceive of the sand on a beach, your concept of it does not convey the quantity any more accurately than your concept of stars. Both are numbers your brain files away as very big, and the similarity of their bigness is not actually illuminating about the scale of the universe. What does help, for some people, is not comparison but contemplation. Sitting with the number not as an object to be compared to other objects, but as a statement about the nature of reality. The observable universe is not big in the way a mountain is big, or the Earth is big, or the solar system is big. It is big in a way that is categorically different from all of those things, in a way where the word big no longer quite applies, because big implies a comparison to some standard, and there is no standard large enough. And the observable universe is a tiny fraction of the probably infinite whole. What would it mean to actually see this? To genuinely perceive, even for a moment, the scale of what exists? The closest human analogy might be the experience some people report when engaging deeply with mathematics, or with certain profound experiences of natural beauty, a brief sense of scale that exceeds the ordinary bounds of the ego and leaves a residue of changed perspective. Physicists who work in cosmology for decades sometimes describe a similar effect. The numbers stop being just numbers and start to feel like something, a genuine apprehension of scale that reorients their sense of their own significance. This is not available on demand. It cannot be manufactured by reading a script, no matter how carefully written. But sometimes, in a quiet moment, looking at the night sky, when the sky is dark enough to see the Milky Way as a band of light rather than just isolated points, something of the scale breaks through the ordinary barriers of the mind. The stars you see are a tiny fraction of the stars in the Milky Way, which is a tiny fraction of the galaxies in the observable universe, which is a tiny fraction of the probable infinite whole. Every photon reaching your eye from those stars has been traveling, in some cases for millions of years, across distances that no human has ever physically traversed, or will ever traverse. You are, in that moment, a temporary arrangement of matter that the universe produced, standing on a rock it assembled from stellar debris, looking out at the stars that made you, in a cosmos that does not know you are there, and does not care, but that made you anyway, through a process so long and elaborate and improbable that calling it anything other than extraordinary seems inadequate. The infinite universe is terrifying because it makes you small. It is also the reason you exist, because a universe finite enough to not repeat configurations, a universe too small and too brief to produce complexity, might never have produced you. The infinity that terrifies is also the infinity that enabled. The same enormous scale that reduces your uniqueness to a local fact is the scale that gives the universe room enough and time enough to do the extraordinary improbable work of producing something that notices. That is the reason, as much as a reason can be found. The universe is infinite because it is the kind of universe that produces everything that can be produced. And one of the things it can produce, in the right corner with the right constants at the right moment in the right bubble, is something that looks outward and wonders about the whole.